Well, thank you. The interesting thing about composite materials is their properties are not just an average of the properties of the constituent materials, and it's an interesting mathematical question: what properties can you achieve with composite materials by mixing materials together? And there's a lot of surprises in store that when you consider what you can actually get. For example, the stained glass windows that you get, the brilliant red color of stained glass windows is actually due to small gold particles that are embedded in glass. And of course, glass is transparent and gold is yellow. And how do you get a red color? And it's not due to chemical reaction or anything like that. It's just due to the composite structure, the interaction of electromagnetic radiation with small metal spheres of gold. And different metals give rise to different colors. And so in the last 15 years, there's been interesting a class of composite materials which are known as metamaterials. And they combine the most interesting properties of composite material are when you combine materials with very different properties, such as a good conductor and a poor conductor, or something which is stiff, which is something which is compliant. And the work I'm going to speak about is joint work with Marc Brion, Andrei Shakayev, Fernando Guevara, Vasquez, Daniel Onofre, Pierre Sepachet, and John Willis. But first of all, what is a metamaterial? And the phrase was first coined by Walser in 1999, and he said they're macroscopic composites having a man-made three-dimensional periodic cellular architecture designed to produce an optimized combination not available in nature of two or more responsibles to a specific excitation. That was a bit complicated, and what is two or more responses? And a simplified definition was by Browning and Wolff in 2001, and they're a new class of ordered composites that exhibit exceptional properties not readily observed in nature. And in fact, the constraint that they have to be ordered is not really important. But I want to give you some examples. First of all, just to begin with, about high contrast elastic materials with unusual static behavior. And if you look at the landscape of isotropic materials, their linear elastic properties are characterized by two moduli: the shear modulus, which is the resistance to shear, and the compressibility or bulk modulus, which is the resistance to compression. So if you've got materials with low shear and low bulk modulus, so spongy materials, rubbers have high bulk modulus and low shear modulus. Rigid materials have high bulk and shear moduli. But the interesting materials are materials in this corner here, which could be called dilational materials or exotic materials that are not ordinarily found in nature. And they're materials for which the bulk modulus is low, but the shear modulus is high. So in two dimensions, a material which has got this property, the easiest deformations are conformal deformations, actually. And so Roderick Lakes actually experimentally in 1987 demonstrated the existence of such materials. If you take an ordinary foam and you stretch it, it actually gets thinner. Whereas these dilational materials, if you take a foam of one of those, you stretch it and it gets fatter in the middle, actually. And this is due to the microstructure of this particular type of foam, that it's got a reentrant microstructure. So as you pull it, the structure unfolds and it gets fatter, actually. And so a material with a Poisson's ratio close to -1, that's the extreme example of a material with low bulk modulus and high shear modulus. An example of what I call a unimode extremal material. And it's compliant with respect to one strain, dilation, yet stiff with respect to all other orthogonal loadings, namely all shears. And in elasticity in 3 dimensions, the elasticity tensor is represented by a 6x6 matrix that links together the stresses with the strains. And for this particular material, the elasticity tensor has 1 eigenvalue which is small and 5 eigenvalues are large. And a natural question is, can you get other sorts of extremal materials which have got one set of large eigenvalues and another set of small eigenvalues? In particular, can you get one with 3 eigenvalues which are small and 3 eigenvalues which are large? And the simplest geometry is a laminate material, and if you've got very stiff material mixed with very compliant material, it's easy to take this material and you can easily shear it back and forth in this direction. You can also easily compress it back and forth in that direction. And if we're in 2 dimensions, however, it's stiff against this sort of loading, actually. So in 2 dimensions, this has got 2 easy modes of deformation, 2 small eigenvalues, but 1 large eigenvalue. In 2 dimensions, the elasticity tensor is represented by a 3x3 matrix, actually. And in 3 dimensions, such a laminar is actually a tri-mode extremal material, because you can also deform it easily in this direction out of the board as well. And so this material here was rather special in that the loading that it supported was uniaxial. In other words, the stress, which is represented by a symmetric 2x2 matrix in 2 dimensions, has just the stress that it supports is a rank 1 matrix. If we consider other geometries, such as this one here, this geometry here is stiff if at the same time we push it in this direction, we push it in the orthogonal direction at the same time. And that's a bimode material. It's got 2 easy modes of deformation, and it supports 1 loading. And that loading that it supports is represented in 2 dimensions by a 2x2 symmetric matrix with positive determinant. If we take this inverted honeycomb material, this is a material which is stable if at the same time you push it in this direction and pull it in that direction there. And so that actually supports a loading with negative determinant. And so those were bimode materials. You can get unimode materials quite easily through laminate type structures here. So this is the dotted region here is compressible materials. This is sort of like fairly rigid phases. And this material here, you can shear it in this direction here, but there's, and this will change its orientation as you shear it. And so there's 1 easy mode of deformation, and that's characterized by a strain with negative determinant. And you can mix this, take this structure here and mix it with itself to get this herringbone structure. So here, this is fairly stiff material, but not completely stiff. This is stiff material, and here you've got compliant material. And when you pull this in this direction, this unfolds and it expands in the other direction. And so this structure here is an example of a material with negative Poisson's ratio. And in fact, if you look at the performance of that material with bounds of Shakaev and Gibiansky, these are upper and lower bounds on the Poisson's ratio, which measures when you pull it how much it expands in the other direction. This is the performance of that structure relative to the bounds, and as it gets very close to the bounds which must hold for all possible structures, actually. And in particular, if you're interested in negative Poisson's ratios, so that a material will actually expand when it's stretched, you can see that you need a very large, very small stiffness ratio. And so you need extreme properties when you're combining materials together. And this is a related structure of Larsen, Sigma, and Boystra. And so this is, again, sort of voids, and this is sort of stiff inclusions here. And when we pull this in this direction, if I pull this in this direction, this will expand outwards. And again, you get something with a negative Poisson's ratio. And then you can play around with these things. You could take a simple laminate and combine it with this unimode material that we had before to get something which is a bimode material. And this actually supports a stress with positive determinant. And you can play these tricks in 3 dimensions as well. And the basic building block is what we call a pentamode material. And the pentamode material has got a structure like a diamond. This is a unit cell, and the thing is periodically repeated. And then as you move and this supports one loading. In other words, it's the periodic version of this supports one loading. It's stiff with respect to one sort of external force. Or stress field, and if I move the point P within the unit cell, I can get all sorts of anisotropic properties. And we came up with this material, and we never thought no one would ever build it, but the group of Martin Wegner et al. Actually built this material recently, and so this is sort of pentamode material, and this is using a lithography technique in 3-dimensional lithography technique with lasers, and with 2 types of lasers, one to excite the photoresist and another one to de-excite it to get very fine structure. So this material here is a little bit like a liquid, that it's very easy to shear, but relatively difficult to compress with uniform compression. And as you make this structure isotropic, it's resistant to not just hydrostatic compression, but to a mixture of shear and compression, actually. And these are numerical results. What controls things is the thickness of this junction here. As you vary that thickness of that junction, you get the figure of merit, which is the ratio of the bulk to shear modulus, gets better and better the thinner the junctions. And this is where that experimental result was, with a figure of merit of about 10 cubed. About 1,000 of the difference between the bulk and shear moduli with that particular material. And so if you've got your pentamode materials, which are resistant to loadings, what you can do is you can take this structure here and superimpose another structure like it, which supports a different loading. And in this way you can develop, and then you bend the links to avoid intersections, so that so by superimposing those pentamode materials, you generate all possible unimode, bimode, trimode, and quadrimode extremal materials. And then having obtained the extremal materials, which have elasticity tensors with very large and very small eigenvalues, then you laminate them together to obtain a material with any desired 6x6 symmetric positive definite matrices as the elasticity tensor. So using these materials which have very extreme properties, almost rigid and almost compliant, you can build any elasticity tensor. So this actually shows that all elasticity tensors are realizable, and Kamara and Sepichet went further and actually characterized all non-local responses as well. So that's sort of static behavior, but you can get very interesting dynamic behavior as well with elastic materials and masses. And I just wanted, this is not the usual way Maxwell's equations are written, but it's interesting if you write Maxwell's equations in this way, you can compare them with the equations of linear continuum elastodynamics. And so this is Maxwell's equations. E is the electric field, epsilon is the permittivity, or the dielectric constant, omega is the frequency, so this is time harmonic at constant frequency, and Cijkl is given by this formula here in terms of the magnetic permeability tensor, and epsilon Eijm is the completely antisymmetric Levi-Civita tensor, taking values +1 or -1, depending on whether it's an odd or even permutation of 1, 2, and 3. And so, in particular, if you switch the indices I and j, this will change sign. So this tensor C here is antisymmetric with respect to switches of the first pair or second pair of indices. That's in contrast to continuum elastodynamics, which looks very similar, but the elasticity tensor here is symmetric in respect to switching I and j and k and l. And here, U is the displacement field, which plays the role of the electric field. And it looks like the density plays the role of the dielectric constant. But that's rather interesting. That actually suggests that the dielectric constant and the density might have similar properties. And why is that interesting is that it's known that the dielectric constant actually depends upon frequency. And this would suggest that the density entering in the wave equation for continuum elastodynamics should depend upon frequency. And also the dielectric constant can actually take negative values in metals such as silver and gold in the optical frequencies. And so that would suggest that the density could take negative values as well. And and also the dielectric constant be anisotropic, which suggests that the density can be anisotropic as well. And so just like the effective dielectric constant is not a volume average of the local dielectric constant, so too one should expect that the effective density is not necessarily a volume average of the local density. So that the conventional law of mass transmission of sound doesn't hold. And actually back in 1980, Berryman found an approximation scheme that predicted a different law for the effective densities. So that the effective density is not just a volume average of the two densities, but is given by this complicated formula here. And actually in 2006, Liu, Wen, and Sheng provided experimental demonstration for aluminium cylinders and air. So this was the wave velocity, and this was the experimental results up here, and these are the results if you assume that the density was just a volume average density. And so there's a big difference actually. And the reason that the effective density is not just a volume average of the density is the fact that the fluid and solid, in this case the air and the aluminium cylinders, when sound propagates through, don't move together actually. They have different velocities. And actually Sheng, Zhang, Liu, and Chan in 2003 found that materials could exhibit a negative effective density over a range of frequencies. And so this was an experimental result, but the geometry they basically had was they had lead balls surrounded by rubber in a stiff matrix. And when you oscillated this back and forth at a given frequency, the lead balls, there was a resonant frequency, and the lead balls moved out of phase with the motion of the surrounding background. So when the velocity of the rigid material was in this direction, the lead balls were moving in this direction there. And so they had a momentum which was opposite to that of the velocity of the surrounding material. And so effectively they had a negative density. And mathematically the observation goes back to Zhikov in 2000 and also Bouchetté and Feldbach in 2004. And actually there's a close connection between negative density and negative magnetic permeability. So this is a split ring structure of David Smith, and this is to get materials with a negative refractive index. And so here you've got a split ring structure, and that interacts with a oscillating magnetic field, which causes the electrons to move back and oscillate back and forth around the rings, and that changes the magnetic permeability of this material actually. And that's because the same equation, the Helmholtz equation, governs the behavior of both anti-plane elastodynamics and transverse electric and transverse magnetic electrodynamics, that if you take this split ring resonator structure here and oscillate and make things elastic, so this is void in this material here, this is sort of stiff material here which has got some mass, and this has got some mass here, that if you oscillate this back and forth in this direction, the mass in the middle travels in opposite direction to the surroundings, and it gives one a negative effective density. And actually, this behaves like an acoustic band gap material, and that was noticed by Movcho and Ganau in 2004. And so a simplified one-dimensional model is you could just take a bar, which is rigid, and with very little mass, and you have voids and mass in the middle, and these are connected with the ends of the cavities by springs with some spring constant K. Then it's an elementary calculation to show that the relationship between the momentum and of the system, which is given by the masses here, and the velocity of the surrounding material is given by P is equal to mv, with m given by this formula here. And then what happens if the frequency is large enough, this denominator comes to being close to zero, and it can become negative, and so you can get a negative effective mass actually. And actually Schoenberg and Sen found that a laminar of two fluids would have an anisotropic density, and Bouchetté and Feldbach in 2 dimensions, and Avila, Grisot and Miara in 3 dimensionals essentially proved that materials could have an anisotropic and negative effective density. And so this is a simplified model where you end up with a material with anisotropic density. So you end up with, you have a surrounding material which is rigid and light, and you've got cavities with springs in this direction which have got one spring constant K, and springs in this direction which have got a different spring constant L. And when you oscillate this back and forth in this direction, it has got a different inertial response to if you oscillate it back and forth in this direction there. And the springs could have some damping. They could be viscoelastic, in which case the effective mass will actually be complex valued.
What do hidden circles mean?
Okay, so yes, what I mean by hidden here is that there's some mechanism in here, but if I'm just interested in the overall macroscopic response, I might not know that these inclusions are here. So, so they are hidden from the viewpoint of they're from the macroscopic viewpoint, they're not important. And actually, you could vary the model a little bit to rotate these so that you've got different spring constants, but at different angles in the different voids. And in this case, the eigenvectors of the effective mass density can actually rotate with frequency. And so it'd be interesting to see what sort of applications of such a material could be, but that hasn't been explored yet. And actually, not only can one have a frequency-dependent mass, one can also have a frequency-dependent moment of inertia in a seemingly rigid body. So from the outside it looks rigid, but it's got this spinning top inside it, and then that actually gives rise to a frequency-dependent moment of inertia when you work things out. So now I want to talk about one of the interests in metamaterials is through transformation-based equivalent media and cloaking, and so this arose in the context of electrical impedance tomography, and the basic idea is that you have a body, in this case the body of Gene Isaacson, to which electrodes were attached, and you apply voltages around the body and measure the corresponding currents, and the question is, what can you say about what's inside the body? And so this is an example, and this is an experiment here in 2 dimensions, and this is meant to represent lungs, and this is the heart or something like that. And these have different conductivities, and then from the exterior measurements, one can sort of recover what's inside. It's actually an ill-posed problem, but Ullman and Sylvester actually proved that that you could recover the conductivities inside, provided they were bounded and not anisotropic. But later, Greenleaf, Lusses, and Ullman in 2003 for conductivity, which was later extended to 2-dimensional geometric optics by Leonhardt and to Maxwell's equations by Pendry, Schurig, and Smith, found out that this wasn't, there were things that you couldn't detect that would be invisible from the outside, and their basic idea was that the equations of electrical conductivity retain their form under coordinate transformations. And so if you take a coordinate transformation from this geometry here to this geometry here, then what you find out is that the 2 problems are equivalent, provided if the conductivity was isotropic in this geometry, you got an appropriate anisotropic value of the conductivity in this geometry here. And in particular, you could take a transformation like this one here, where a point is blown up into a disk, and then lines of electrical current flow along these grid lines get transformed into electrical current flow, which goes around the disk in that form there. And so if you put an object inside here, it doesn't disturb the surrounding current flow. Because putting an object here is basically equivalent to putting an object inside this point. And so that was the idea of coordinate-based cloaking. And Pendry, Schuring, and Smith did the same thing for electromagnetism, including, this is for showing light rays, but basically it's the same idea. And you can put an object inside this region and it will remain cloaked from the outside. And this was experimentally realized by Schurig, Morris, Justin, Kommer, Pendry, Starr, and Smith in 2006 with this geometry using metamaterials to get the artificial magnetic behavior that are needed for the anisotropic properties of the material surrounding the cloak. So here, again, is this split ring resonator type structure. And these are the experimental results. This is and numerical results. This is the ideal cloak, showing the waves not penetrating the material inside, but passing around the cloak. And unfortunately, this sort of cloak is difficult to achieve in practice, and so they actually had a modified cloak which had the properties that in the geometric optics limit for rays that it would behave in an ideal manner. And their approximate cloak had moduli electrical permittivity given by this and magnetic permeability given by this. And this is the numerical simulations, so it doesn't behave perfectly anymore. And in particular, there's a little bit of a shadow zone there and reflections in this direction here. But these are the experimental results, which are meant to be compared with this one here. And the waves actually pass quite through, as opposed to when the cloak is absent. And these are the experimental results that you end up with much more scattering and more of a shadow zone behind the object. And then later it was realized in 2011 that one could get much simpler cloaks. In particular, just a piece of calcite would do the trick. And the idea was to use a deformation which was piecewise constant, and which mapped this region here into the region with this vanishing, actually. And so this was just a constant anisotropic dielectric tensor here and a constant anisotropic dielectric constant here, which could be mimicked by crystals of calcite. And so here you've got a pink rod which is being cloaked by the calcite, actually. And similar experiment by Chen et al. In 2011 was based on the same idea. And here they demonstrated the letters of the alphabet would be jumbled up if the cloak was absent, but in the right order if the cloak was present. And actually the same arguments apply to the acoustic equation as shown by Kummer and Schurig, Greenleaf et al., Chen and Chan, Kummer et al., and Norris in 2008. And these require a cloaking shield of fluid with anisotropic density and appropriate bulk modulus. So materials with anisotropic density have application to cloaking, actually. And so this was numerical simulations of cloaking of water waves by Nicolette et al. In 2008. And so here you've got a point source, and this is the object which is being cloaked, and the waves go around it without being scattered. And they did experiments with water waves, and it's not quite so clear, but this is without the cloak, and there's a little bit more scattering around here, and with the cloak there's less scattering. And then for acoustic cloaking, Zhang, Xie, and Fang in 2011 obtained this sort of cloak here, and this is scattering of a disk with respect to acoustic waves. And again, you get a substantial shadow zone. If you put the cloak around it, you reduce the shadow zone considerably. So there was a different sort of cloaking that myself and Nikolai Nikorovici came up with at the same time, actually a little bit before, which is a transformation optics type cloaking, which was associated with superlenses. So the idea of superlenses was to use a coordinate transformation which folds space. And this is an interpretation of Leonhardt and Philbin in 2006. And so if you fold space, 3 points get mapped to a single point. And so if you have a field here, you will end up with a mirror field here and a mirrored field there. And a single field in this geometry here. And when you do that coordinate transformation, you find out that the material inside this slab, inside this dotted region here, corresponds to a material with a dielectric constant of -1, a magnetic permeability of -1, and a refractive index of -1. And this is known as the Veselago lens. And Pendry in 2000 made the bold claim that this would behave as a superlens. In other words, that it would actually focus, be able to, capable of sub-wavelength resolution. And Veselago realized that if you had a source here, the fact that you had a negative refractive index would imply that rays, the image showing here, would get refocused, bent back here and refocus, and then negative refractive index would get bent back and refocused again. And what was subsequently realized was the field here is a reflection of the field here, which is a reflection of the field there. And so Pendry claimed if you had a point source here, you would have a point source over there. And but that actually causes some mathematical problems, because if there's a point source over there, there must be some singularity. And there can't be a singularity if there's no sources there. And so what was actually found to happen by Garcia and Nieto Vesperinas and Podgorski and Efros, that there's actually divergent fields between these ghost sources. And this is your point source here. This is the slab lens or the Veselago lens, and things get refocused at this point here, and there's oscillations in the field in this direction there. And this is numerical results of Kummer showing that these regions here, these are called surface plasmons, but they're basically what we call anomalously resonant regions on both sides of the lens. And it's actually the length scale of these surface oscillations which sets the scale of resolution, not the wavelength of the light or the radiation that you applied. And Fang Li, Sun, and Zhang in 2005 experimentally demonstrated that these could resolve finer than the wavelength. And so this is the word nano, which is inscribed. This is the resolution using the superlens, and this is the resolution without the superlens, actually. And so actually you end up with a peak of width 89 nanometers, and as opposed to without the superlens of 321 nanometers, and this is sub-wavelength actually. And what we found is that you had an unusual sort of cloaking associated with this. So so this is actually associated with a simple equation that I have this geometry, and my equation is equals 0 in the absence of sources. And here, epsilon of x, which is the dielectric constant, takes the value epsilon of x equals 1 here, epsilon of x equals minus 1 plus I delta, where delta is a very small constant, and epsilon of x equals 1 outside here. And so in the regions where epsilon of x is constant in these three regions, this just says that the Laplacian of v is 0, so it's the real part of an analytic function. And so this is the geometry that we had. This dashed region here is not a physical boundary, but is actually what we call the cloaking region. And what happens is that we've got a uniform field at infinity, and we've got dipole sources here, which you think of them as poles, if you like, with a residue which is proportional to the field acting on them. And what happens is that these dipole sources, which you could think of as particles or polarizable particles, when they actually come within this dashed region here, they become invisible. So it crosses the boundary here, and what's happening is in this region here you're getting enormous fields which are cancelling the field acting on these particles, but outside it's as if they become invisible. And this is with a cluster of 7 polarizable dipoles, and once it enters this cloaking region it becomes invisible, and then when it exits the cloaking region it appears once again. And so all of the it stopped anyway. That's and just for fun, we did it with an Aston Martin, or the trace of an Aston Martin, which became invisible as well. So that's for people that like James Bond. So what about elasticity? Can one get cloaking for elasticity? And we looked at this question back in 2006, and our idea was to apply the Greenleaf-Lassus-Ullmann Pendry-Schulwig-Smith method of cloaking to elastic waves. And again, this requires materials with anisotropic density. And what's interesting about elastodynamics is that the equations are not invariant under coordinate transformations. So that if you take the equations of elastodynamics, rho is the density, sigma is the stress, which is the elasticity times the gradient of the displacement, and you do a coordinate transformation, then after the coordinate transformation you end up with new equations which don't have the same form as the original equations, but have additional coupling terms, like this tensor D here and this tensor S here, which are given by these formulas. And one has a density rho prime, which is anisotropic, even if the original density was isotropic. And but how do you get these coupling terms, and what do these mean actually? And so those new equations don't look like elastodynamic equations at all, but actually they're a special case of equations that John Willis obtained for composite materials. And he was looking at ensemble averages of composite materials, and noticed that the macroscopic equations took this form where sigma is the stress, p is the momentum, epsilon is the strain, and u dot is the velocity. And so he found out that the average stress, ensemble average, depended not only upon the strain but also upon the velocity, and the momentum just didn't depend upon the velocity but also depended upon the strain, and actually they were sort of coupled together. And and the star here denotes a convolution actually. But for the purpose of cloaking, you'd actually like to get a constitutive law to be local in space and to apply to a single realization rather than an ensemble average. And so you could ask the question, are there composite materials where such a constitutive law is realized? And indeed there are, but I just noted in passing that Brun, Gounod and Movchan in 2009 have shown that one can obtain cloaks with S equals D equals 0 and with C not satisfying the usual symmetries. And so you can avoid the coupling terms if you allow elasticity tensors which don't satisfy the usual symmetries. And that transformation was generalized by Norris and Shuvaloff in 2011. So what's the idea to get such materials is that an electric dipole array of positive charge and negative charge in an array like this generates a polarization field. The analogous thing for elasticity is that if you have a force dipole array of forces in this direction and forces pointing in this direction, they actually generate a stress field. So if you take your material with negative effective mass with your material with positive effective mass, and here this is negative effective mass and positive effective mass, when I accelerate this, because this has positive effective mass, I'll feel an inertial force in this direction. This has negative effective mass, so I get an inertial force in this direction. And so I end up with force dipoles, actually. And so accelerating this material with no strain gives stress. And so this is an example of this sort of Willis-type material which lies outside continuum elastodynamics. And you can do the same thing with models with springs and balls and analyze it more directly. And again, you've got something with positive mass and negative mass. And when you accelerate this will you get a force in this direction. This has negative mass. This would this one and this would have this force, and so this pulls this apart, which will generate stress in the material. So one question is, using these techniques of transformations, can you apply them to discrete networks? Because any solid you can think of as a network of springs with masses and things like this. So can you apply these transformation ideas to networks instead of continuum materials? So if I have a network where this is a terminal node, the black things here are masses and the straight lines are springs. If I've got a force in this direction, the idea is to transform this network into some other network by changing the position of all the nodes and keep the masses the same, and keep the forces just to translate them to the new geometry. And so if I had a force acting along this in the direction of the spring, I would have a force acting here at an angle to this spring. And but that's a little bit odd. If this is going to be physically realizable, I'll need a new type of spring. A normal spring, when you pull it, the forces are in line with the spring. They're equal and opposite at the ends of the spring, but they're in line with the spring. Can you actually obtain a spring where the forces are equal and opposite, but not aligned with the spring itself? And the answer to that is yes, and it's what we call a torque spring. And the forces at the ends are equal and opposite, but they're not aligned with the line joining the terminals. And this is example of a torque spring, and so this is our terminal nodes where we apply the forces. These are ordinary springs, and this is just a node with no mass attached at these points here. And here at the ends here we've got the masses, and so this is oscillating at fixed frequency, for example, and the arrows here denote the forces, and so we've got balance of forces at these nodes here, that all the arrows sort of balance one another, and the mass imparts an inertial force which counters the force in the spring, so you've got equilibrium there. But at these sides here you've got the force acting here, which is opposite to the force acting there, but is not aligned with the line joining the two terminal nodes, actually. And so, and this is without gravity. If you include gravity, you'd it would mess this picture up, actually. But so that's one example of a configuration of a force spring. This is another example. And again, the straight lines just denote springs. And here you end up with a force acting on this direction and a force acting in this direction there. And these M's are the masses, which have got inertial forces. And so if you ignore the structure in between, I have two terminals where the force acting on them are equal and opposite, but not on the line joining through them, actually. And so more generally, we've asked the question, if I've got any network of springs and masses, can I characterize all the possible responses as a function of time for, and this is with Daniel Onofre and Fernando Guevara-Vasquez, and what actually we find out is that we're actually able to get a complete characterization of the possible responses within linear elasticity as a function of time of spring mass networks with an arbitrary number of terminals, not just two terminals here. This is just an example with two terminals. And you can actually get metamaterials with zero effective mass density but a frequency-dependent elasticity tensor, and the idea is to replace each spring with this type of geometry here. So there's springs here, and we've got some square of springs here and masses attached to this end here, and so if I pull this in this direction here, this will excite these masses there, and so the internal mass influences the elasticity tensor, the stretch, but does not add to the effective mass, because if I take this same geometry and I find out that I can, within linear elasticity, translate the ends in this direction or in this direction or in that direction, and the masses essentially don't move. And so small displacements of the terminals don't lead to any inertial force. So it's got a zero effective mass density, but nonetheless it's excited under stretching. Anyway, it's constantly a surprise to find what properties a composite can exhibit. And so one final example is in elementary textbooks, one is told that in classical physics the sign of the Hall coefficient tells one the sign of the charge character. So the Hall effect is when you've got a magnetic field and you have electrons flowing along, that the electrons feel a force which is perpendicular to the magnetic field and to the velocity of the electrons, and it depends upon the charge, and it's usually known that, well, people take it for granted that within classical physics, you can work out the sign of the charge carrier by measuring the Hall coefficient, which measures that effect, that additional voltage that arises. But using composite materials, you can get a counterexample to this, and the geometry looks like this. And actually, when we came up with this geometry, we just came up with a two-dimensional version of this geometry. And it was an artist, Dylan White, who had a website, and we were interested in, it looked like armor to us, like medieval armor, the sort of intellect chains and things like this. And Dylan White actually specialized in selling and making this sort of medieval armor. And the geometry that we considered actually correspond to a geometry of Japanese medieval armor. And he suggested, why don't we look at the three-dimensional version of this? And this is the first few layers of the three-dimensional geometry, but this is the period cell. And what you have here is highly conducting rings, and with something with cubic symmetry, and in the gaps, if this has got higher electrical potential than this one here, or this has higher potential than this one here, then in the gaps, the electrical potential is in the opposite direction, actually. And so if I put my material with high Hall coefficient in these gaps, I'll actually end up with a composite which has got opposite Hall coefficient than is expected. And actually we're able to prove that rigorously. And so some experimentalists are now interested in trying to do the experiment on that, actually. And anyway, thank you very much.